Okay, so we're going to keep working on some of these examples. And again, it assumes you know nothing about physics. So some of the things that we're going to do might be more elementary than what you've already seen if you have a stronger physics background. So then that's fine. It's just another way that you can apply, this concept to something you already know. Okay, so one application of this is letting vectors. Remember, vectors stand for a directed line segment. Velocity makes a great way to or application of vectors, because velocity, by definition, has a certain magnitude, like how fast are you going, and in what direction, and so that's a vector. And again, those with physics background know that speed, being the absolute value of velocity, has no direction. It's just a scalar, where velocity not only doesn't matter how fast you're going, but it also matters like in what direction. Okay. So notice that an airplane has a speed of 400 miles per hour. So right there, it doesn't give us any indication of a direction. But then if you read further, it says in a southeasterly direction. And you sort of have to assume this problem, that it means exactly in that southeast direction. So this is north, south, east, and west. Exactly southeast would be like a nice little 45-degree angle. In that direction right there, so 45 degrees. Otherwise, we wouldn't be able to understand, or we wouldn't be able to solve this problem. Okay, so the plane is going in that direction. There's a wind blowing at 45 miles per hour in an easterly direction. So easterly direction means from the west going towards the east. We have this wind blowing. Okay, so find the speed of the airplane relative to the ground. Well, like the plane in like whatever the odometer or the speedometer or whatever it is in the plane, it's going to register 400 miles per hour. But if there's a side wind or a tailwind, something that's going to either help that plane go faster or maybe work against the plane, then when you compare it to the ground, like how long did it take you to get from point A to point B, that's going to be that would be different. That's going to be a result of multiple forces. Like it could be the wind, it could be I don't know, other things, but mostly just the wind in this case. So let's take a look at that 400 miles per hour in hindsight. That was super awkward. Sorry about that. So if I think about 400 miles per hour, that's the magnitude of that vector. So if I'm thinking about this vector going 400 miles per hour, that has two components, and that's where that southeasterly direction goes. So it was over and down by a certain amount. And because it's exactly a southeasterly direction, we can realize that's a 45, 45, 90 triangle. So we have equal increments here. And so if the hypotenuse is 400, x root 2, we could divide that by root 2 and realize that this would be 200 root 2, and this would be negative 200 root 2, at least in terms of those components. And so the vector of the airplane could be represented as 200 root 2I minus 200 root 2J. So this still has a magnitude, remember, of 400 miles per hour. The magnitude of that vector was 400 miles per hour, and in that southeast direction. Okay, let's talk wind. So my wind is has a magnitude of 45, is blowing 45 miles per hour in an easterly direction. So I have this vector that's going here, has a magnitude of 45. So my vector that represents wind has a magnitude, there's our symbol, of 45. And if I think about it, it's just going to the right. So as a component of that component form, it could be 45I and then plus 0J. Now, this wind is constantly, we assume it's constantly blowing this plane. So it's really blowing this plane off course. So if the plane wanted to end up here, it's actually going to end up over here somewhere. And in fact, we can find that exact spot if we just take one of these 45 mile per hour winds and put it right there. And so it's kind of like one of those resultant forces, like the plane's trying to go in this direction and the wind's blowing it over here. So the plane's actually going to end up over here. It's going to just by a little bit. Okay. So if I could find the magnitude of this vector, that's going to give me the speed of the plane relative to the ground. And this magnitude, just by a property of a triangle, like this is going to be a little bit bigger than 400 miles per hour, because that wind is sort of helping it out, because there are some components of this airplane that are going in an easterly direction. So you're getting some extra wind in just that direction. So how do I find that blue vector? Well, we would basically add the components. We would add up, vector that represents the airplane plus the vector that represents the wind to get our new vector that would be the speed relative to the ground. And so, I add up by components. So I've got a 200 root 2I minus 200 root 2J. So that was our airplane. And then a 45I and 0J is our wind. So if I add those up, now I can't really add these up other than maybe grouping them at like 200 root 2 plus 45I, and then minus 200 root 2J. So that's the velocity vector relative to the ground. So that's that blue one. So how do we find its speed? We need to find the magnitude of this. We need to find what is the magnitude of this vector. And again, that's just Pythagorean theorem. It's not the cleanest of numbers, but it's okay. We could find it. So it's the square root of quantity 200 root 2 plus 45 squared. Notice I removed the I because it's just the coefficient, plus, and whether you think of it as a negative or a positive, it doesn't really matter in this case because we're squaring it out. That would give us the magnitude of that vector. Okay, so probably I should have already done this ahead of time, but I didn't. So now you can hear the clicking of my calculator. 200 root 2 plus 45 as a quantity. We're going to square that, plus negative 200 root 2 squared, and then squared that. So I got a magnitude of 432.991. I'm just used to 3 decimals for AP Calc, miles per hour. And let's think about the likelihood of this being the right answer. Like, is it reasonable? We know it should be more than 400 miles per hour because that would be the plane all by itself. The wind is only 45 miles per hour, so I should not get a number that's more than 400 plus 45. And that would only happen if it was an exact tailwind. So some of this wind is not really helping the plane, right? It's not giving, it's not exactly behind it in terms of making it go faster, for a lack of a better comparison. So this seems very reasonable in terms of that. And you think about it, last time we went on a plane. Sometimes the pilot will say, "Oh, well, we got there faster than we thought," because there could have been a tailwind. And so even though your plane isn't like your speedometer is not going any faster on the plane itself, because the wind is helping you go along relative to the ground, you're covering more distance in that same amount of time. So you're going faster. Okay, so let's also talk about multiplying vectors, and we're going to look at 2D vectors in this video, but in the next video we're going to look at 3D vectors. And there's two kinds of multiplication for all vectors really, but for especially 2D vectors, there's something called the dot product, and this is how we're going to multiply two vectors together. And so it's going to be an operation. I'm going to define this operation. So if I have vector, let's say vector v is some components of I and some components of j, and I have vector w that has some components of I and some components of j. And I wanted to multiply these two vectors together using a dot product. And literally, I'm going to use the dot. So dot product. So how do I multiply these together? I look at the I components. I'm going to multiply the A by the C. I look at the J components. I multiply the B by the D and just sum them up. And notice there's no more I's or J's. So this is a scalar. It is not a vector. Okay, so And then part of the reason why we need the dot product is because that's in the definition of how do you find the angle between two vectors. Like if I had a vector going in this direction, let's say vector v, and a vector in this direction, vector w, I want to find a way to figure out what this angle is, and honestly, it should be irrelevant to the size of the two vectors, right? It should have nothing to do with the size of the vectors, because if w keeps extending in the same direction, it's not changing this angle here. And so what I really am interested in is kind of building off of slopes. And so when I get this angle between two vectors, here's what that is. It's going to be defined, first of all, which is, I think, very exciting, in terms of cosine. And I like it in terms of cosine because cosine, like you know your angle can only be between 0 and 180. Because if you say, well, what if you go more than 180? Well, then you can figure out, okay, well, instead of finding this angle, find that angle. So between two vectors, there's always an angle that's going to be 180 or less. I like that it's defined in cosine, because when I start doing inverse cosine for these angles, if it's a positive value, I know it's an acute angle. If it was a negative, it'll be obtuse. And so I don't have to worry about, inverse sine or tangent, which is down here when it's negative. It's only up here, which is great. Okay, so cosine of theta equals the dot product. So it would be v dot w divided out by the product of their magnitudes, v and w. And remember that the dot product is a scalar factor. This is a scalar factor because it's just a distance. This is a scalar factor, so that's just a distance. So overall, this is going to be a ratio. This ratio is going to equal the cosine of theta. So then we can inverse cosine both sides. And even though we're introducing the cosine, because the angle has to be between 0 and 180, I don't have to worry about the other places in the unit circle. It's either going to be in quadrant 1 if it's positive, because it's an acute angle, or quadrant 2 if it's negative, because then it would be an obtuse angle. Okay, and you do have to memorize that formula. And most of the application of the dot product, at least for right now, is going to be finding the angle between two vectors. So that's exactly example 7. It says find the angle formed between these two vectors. So if I think about this point right here, and I go over 2 and up 4, so right here is vector v, and from that same point, if I go over 5 and up 10, I'm not really sure drawing the scale here. So there's vector w. Now, on appearance, this angle in between certainly looks acute, right? Oh, how cute. But I can't really make that assumption. So what I'm going to do is I'm going to set this up as saying, okay, well, the cosine of theta is equal to the dot product divided by the product of the magnitudes. Okay, so dot product, here we go, in action. We're just looking at the i's. So 2 times negative 5 plus the j's, 10 times 4. So the dot product, and then divided by the product of the magnitudes. So for vector v, it's 2 squared plus 4 squared. Remember, it's just the Pythagorean theorem. And then for w, it's negative 5 squared plus 10 squared. Okay, so remember, this is what cosine of theta is equal to. So it's not theta just yet. So 2 times negative 5 is negative 10, plus 40 is 30, divided by 4 squared is 16, 2 squared is 4, so root 20. And then this would be square root of 125. Now, since we're not really finished, this doesn't represent my final answer, I don't really have to do any kind of simplifying with this. I could just type this in and then do inverse cosine of that. So remember, theta is going to be the inverse cosine of this particular ratio. So 30 divided by the square root of 20 times the square root of 125. Now, this is a positive ratio, and I know that a cosine with a positive ratio would be in the first quadrant. So I know this is going to be an acute angle. And I'm going to put my mode, actually, we do so much in radians. I'm actually put my mode in degrees just so I can get a more intuitive, and like feeling of how big this angle is. I think with degrees we have a better, just a more natural, more natural feeling or understanding about, oh yeah, this looks reasonable. So I got theta to be 53.130 degrees. And again, we assumed it, or not assumed, it looked like it was going to be an acute angle. I like 3 decimals. Putting the 0 here indicates that I went out to that third decimal. It is a significant figure or a significant value. Okay, one more example. It says, now, suppose you don't know all the components. Oops. There's a K here, but we want them to be perpendicular. Well, perpendicular means that the two angles are going to form 90 degrees. So, again, I can still think about drawing these, and maybe I'll draw W first. So over 14 down 20. So over 14 down 20. So here represents W. And then if V goes over 3 to be perpendicular, it looks like, yeah, I'm going to have to go down, right? Like that seems to be, like if I can make that a 90-degree angle, this is V and this is W. The thing is, I don't know exactly, so I'll call that -3, call that K. This is 14 and this is -20. It seems like, yeah, like that's where that would be to make that 90 degrees. So I'm still going to start with my formula. Cosine of theta, just as a good reminder, is equal to dot product divided by the product of the magnitudes. And so then I know I want cosine of 90 degrees is equal to, so dot product, so look at -3 times 14 plus, and then K, that coefficient, times -20. All divided by the magnitude of V, so the square root of -3 squared is 9, plus K squared, times 14 squared, I believe, 196, plus -20 squared, 400. Now, you probably already noticed this and how great this is with cosine, because cosine of 90 degrees is 0. So feel free to smiley face that up. There we go. And so -3 times 14 is -42, minus 20k, all over sort of a messy denominator, but doesn't really gonna matter because when that's equal to 0 and I just multiply this over, it's irrelevant. So I just get 0. That's nice. So 0 is equal to -42 minus 20k. Let's go ahead and solve that for k. So we could add 42, divide out the 20, -20. And so it looks like that's -21 over 10 is equal to k, or -2.1. Now, big takeaway, big idea, perpendicular. And here's another application perhaps of that dot product because of just what happened. If you want two vectors perpendicular, think about that for a second, right? If you want two dot product, if you want two vectors to be perpendicular, aka 90 degrees, and the cosine of 90 is always 0, and our formula is based on the dot product on the top and the magnitudes on the bottom. If this thing's always 0, then this is irrelevant, right? It's just the dot product that matters. And so that's a great application of the dot product and checking, is our two vectors perpendicular? So I'm going to write that down, that if the dot product is 0, then the two vectors are perpendicular. And this is going to be true even when we look next the video at three-dimensional vectors. If the dot product is 0, then we know those two vectors are perpendicular. Okay, so I think that's all I want to do in this video. Then the last video, or I don't know if it's going to be the next video, I'll talk about like three-dimensional vectors and also how can we use vectors to represent a very elementary model of work, again, not as robust as we see in physics class, but still something that would be a great application.